The antennas are already pointed, not searching, not scanning, just listening to a precise location in the sky that appears completely empty to the human eye. There are no visible stars, no planets, nothing that suggests anything is even there. And yet engineers are waiting for a signal that has traveled for more than 20 hours across interstellar space. When the transmission arrives, it isn't silence. In some ways, that would have been easier to understand. Instead, it's something far more unsettling. Structured data that no longer makes sense. The signal is still there, still arriving with the same delay, still carrying information, but the meaning inside it has been lost. On November 14th, Voyager 1 didn't stop talking. It continued transmitting exactly as expected, but for the first time in nearly half a century, NASA could no longer interpret what it was saying. It wasn't a system failure in the traditional sense. It was something stranger, a breakdown not of communication, but of comprehension. And the real danger behind this moment didn't begin billions of miles away. It began 47 years earlier when NASA launched a spacecraft into conditions it didn't fully understand. Voyager wasn't built for safety. It was built for exploration at the edge of what was considered possible. And from the moment it left Earth, it was exposed to forces that could damage it in ways that wouldn't be obvious until decades later. This wasn't a mission defined by a single risk. It was a sequence of exposures: radiation, distance, cold, and time. Each one slowly testing the limits of a machine that was never designed to endure all of them at once. What we are seeing today may not be a new failure at all. It may be the final stage of a process that began the moment Voyager entered its first truly hostile environment. To understand what's happening now, we have to go back to the beginning, to the point where NASA realized they hadn't just launched a probe into space. They had sent it into something far more dangerous than they expected. The first real test came at Jupiter, a planet whose beauty hides one of the most extreme radiation environments in the solar system. Surrounding it is a massive magnetic field that traps charged particles and accelerates them to extraordinary energies, creating radiation belts that are thousands of times more intense than anything experienced near Earth. For a human, entering this region would be instantly fatal. For Voyager, the danger was different, but no less serious. Instead of physical destruction, the threat came in the form of constant invisible impacts, high-energy particles striking the spacecraft's electronics and altering them at the smallest possible level. These impacts cause what engineers call bit flips, where individual pieces of digital information change state unexpectedly. A single flipped bit might seem insignificant, but in a system that relies on precise data processing, even the smallest change can lead to incorrect outputs, corrupted memory, or behavior that no longer reflects reality. As Voyager moved through Jupiter's radiation belts, its systems began to show signs of stress. Data anomalies appeared, signals fluctuated, and for brief moments, the spacecraft behaved in ways that suggested its internal systems were being disrupted. It didn't fail, and it didn't stop functioning, but it wasn't passing through unchanged. What makes this moment important is not what happened immediately, but what it left behind. Those early exposures introduced tiny, almost undetectable forms of damage, subtle vulnerabilities in the spacecraft's memory and circuitry. At the time, they were manageable, but they never fully disappeared. Decades later, as engineers examine the strange patterns in Voyager's current signal, there is a growing understanding that these early interactions may have set the stage for what we're seeing today. The spacecraft didn't just survive Jupiter, it carried the consequences of that encounter with it, all the way into interstellar space. Beyond the outer planets lies a boundary known as the heliopause, the point where the influence of the sun gives way to the conditions of interstellar space. Crossing this boundary is not just a change in location, it is a transition into an entirely different environment, one where the protective effects of the solar wind no longer exist. Voyager crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. What it encountered there was not emptiness, but a constant stream of high-energy cosmic rays, particles that originate from distant astrophysical events and travel across the galaxy at nearly the speed of light. Without the sun's protection, Voyager is now exposed to this radiation continuously. Every moment it moves forward, its systems are being impacted by particles capable of penetrating its shielding and altering its internal state. This process is not dramatic or visible, but it is relentless, and over time, it accumulates. The current anomaly appears to be centered in the flight data subsystem, the system responsible for collecting and formatting the spacecraft's data before transmission. This system is still operating, but the data it produces no longer corresponds to the actual state of the spacecraft. Instead of reflecting reality, it is generating structured but incorrect information, suggesting that part of its memory may have been corrupted. This is where the situation becomes particularly complex. The patterns observed in the data are not random, which would suggest total failure. Instead, they indicate that the system is functioning within a distorted framework, possibly caught in a loop caused by corrupted memory addresses or instructions. At the same time, the human element of this mission is becoming increasingly fragile. The engineers who originally designed Voyager's systems worked with technologies and programming methods that are no longer widely used. The knowledge required to interpret and repair these systems is limited, and with each passing year, fewer people remain who fully understand how Voyager operates at its deepest level. In a sense, the spacecraft is not just aging physically, it is also becoming harder to communicate with in a more fundamental way. As Voyager continues its journey, its power source is gradually declining. The radioisotope thermoelectric generator that provides its energy is losing output over time, forcing NASA to make difficult decisions about which systems to keep active and which to shut down. This process has become a balancing act between survival and functionality. Instruments have been turned off, heaters have been disabled, and entire subsystems have been sacrificed to preserve the spacecraft's ability to communicate. What remains is a minimal configuration designed to extend its life for as long as possible. At the same time, engineers are attempting to correct the corrupted memory within the flight data subsystem. This involves sending carefully constructed commands across billions of kilometers, waiting nearly a full day for them to arrive, and then another day to receive a response. Each attempt is slow, deliberate, and uncertain. Unlike modern systems, Voyager cannot be rebooted in a conventional sense. Its architecture predates the technologies used to repair contemporary computers, and every intervention must work within the limitations of a system designed more than 4 decades ago. The possibility that the system cannot be fully restored raises a profound question. If Voyager continues to transmit data that cannot be interpreted, does the mission effectively end, or does it enter a new phase where communication exists without understanding? In that scenario, the spacecraft becomes something entirely different, a silent messenger, still sending signals into the void, but without a clear way for those signals to be decoded. Voyager was never intended to last this long, nor was it designed to operate under the conditions it now faces. Its continued existence is not just a technical achievement, but a reflection of how far it has been pushed beyond its original limits. The dangers it encountered were real and constant, and the outcome was never guaranteed. Every stage of its journey introduced new risks, and every survival came with a cost that may only now be fully understood. If Voyager were to fall silent tomorrow, it would not erase what it has accomplished. It would simply mark the end of a connection that has already exceeded every expectation placed upon it. Because even without a signal, Voyager will continue its journey. It will move through interstellar space for thousands, perhaps millions of years, carrying with it a record of humanity and a story of exploration that extends far beyond its original mission. The question is no longer whether Voyager will survive, but what its survival has already meant. And when that signal finally fades, the silence that follows will not represent failure. It will represent the point at which the mission became something larger than itself.